In some problems, the curve that we want to integrate over is set up of several connected pieces to form a piecewise smooth curve. So this diagram isn't that great because it's actually smooth all the way through, so you can see that there's a nice curvature all the way through. But say for example, you have a curve made up of several line segments like this, where say this is C1, this segment is C2, this segment is C3. So C would be C1 union C2 union C3. So this is what we mean by piecewise smooth, right? So each individual line segment is smooth. However, here we have a corner, and here we have a corner, so it's not differentiable at the corners. So in a situation where a curve is made up of several components like this and is connected, then we can separate a line integral. So say you want to calculate the line integral over the entire curve, but instead of calculating it directly, you separate it over each individual component and then add all of the integrals together to get the value of the line integral over the entire curve. Okay, so that's in a situation where you want to separate the line integral into smaller line integrals. So let's take a look at an example. So in example 3, you're given this vector field here, and we want to calculate over the line integral of this vector field over a curve C in 3 dimensions, and it's a triangle that connects these points here. So I mean, I didn't plot these points in 3-dimensional space, but you can imagine, say you have 3 points that are oriented in some way, and then if you connect the 3 points to form a triangle like this, you get this closed curve where each side of the triangle can be thought of as a separate curve like this. And so here we have a situation where the entire curve C is the union of each of the individual components. Okay, so we want to calculate the work done by this force field over the entire triangle, but to do that, we're just going to individually calculate over these 3 curves. So let's take a look at curve C1 first. So we need to parameterize each individual line segment, right? So if you remember the formula for parameterizing a line segment is, so the x component would be x1 plus x2 minus x1 times t, and then the y component is y1 plus y2 minus y1 times t, and then the z component is z1 plus z2 minus z1 times t. Okay, so so what do we get as the parameterization? So just plugging in the number. So C1 is connecting these 2 points here, right? So this would be 0 plus 2 minus 0 times t. Then the y coordinate would be 0 plus 1 minus 0 times t. Then the z coordinate would be 0 plus 2 minus 0 times t. Okay, so what do we get? So this is just 2t, and the y component is just t, and the z component is just 2t. Okay, so that's r of t. And then, as usual, t goes between 0 and 1. What about r prime? We're going to need that also for the line integral. So taking the derivative of each, so this is just 2, 1, 2. Right, so just differentiating each component. Okay, so this is x, this is y, this is z, and this is the derivatives. So x prime, y prime, z prime. And again, as I said before, for a line segment, we take t going between 0 and 1. Okay. So now we're ready to set up the line integral. Right, so let's say, call it, we're calculating the work over this line segment. So the integral from a to b, so that's from 0 to 1. What is p? PQR, right? So this is p, q, and r. So we need to plug in x, y, and z, right? So y is t, and z is 2t. So you get t 0, comma 2t. And then dot r prime, which is 2, 1, 2 dt. Right, so let me just annotate that. Again, this is f bar, right? So the vector field, right? So this is p, q, and r, and this is r prime of t. So x prime, y prime, z prime. Okay, so now to calculate this integral, we just need to take the dot product, right? So 2 times t, so it's 2t, and then plus 0 for the middle, and then plus 4t. So it's 2t plus 4t dt. So I'm running out of space, but let's just squeeze it in here. So it's the integral from 0 to 1, 6t dt. So the antiderivative is 6t squared over 2, evaluated from 0 to 1. So plugging in 1, you just get 6 over 2, which is equal to 3. Okay, so the amount of work done over C1 is equal to 3. Okay, so now we just need to repeat the procedure for C2 and C3. So now over C2, again, I need to parameterize the line segment. So we're going from 212 to 210. So let me write it here, 212 to 210. Okay, so the x component would be 2 plus 2 minus 2 times t. The y component would be 1 plus 1 minus 1 times t. And then the z component would be 2 plus 0 minus 2 times t. Okay, so this simplifies to 2, comma, 1, comma, right, because this is just 0, this is just 0, and this is 2 minus 2t. Okay, so that's r of t, and then r prime, derivative constant is 0, so this is 0, 0, negative 2. Okay, so again, we have t going between 0 and 1. So when I set up the line integral, right, so integral over C2 f dot dr, right, so the integral goes from 0 to 1. Now the vector field, so let me copy it down so I don't have to keep scrolling back. So it's y0z. Right, so f was y0z. So right, so hold on, let me annotate so I know what goes where. Right, so this is x, this is y, this is z, this is x prime, y prime, z prime. Okay, so y is 1. This is 0. And then z is 2 minus 2t. Dot r prime is 0, 0, negative 2. Okay, so now we do the dot product, right? So 0 times 1 is 0, 0 times 0 is 0. So all we're just left with is negative 2 times this thing, which is negative 4 plus 4t. Okay, so now we take the antiderivative, which is negative 4t plus 4t squared over 2, evaluated from 0 to 1. And so this is equal to, so when you plug in 1, you get negative 4 plus 2. And then when you plug in 0, this is 0, this is 0, so that's all we get, which is equal to negative 2. Okay, so the work over the second line segment is equal to negative 2. So a negative value for work just means that the force is going against the direction of motion, right? So in the first curve, that means most of the force vectors were sort of in the same direction as C1. However, now in this region here, most of the force vectors are going against C2. Okay, now let's finish up with C3. Okay, so C3, let's remember the points. So it's 2, 1, 0, back to the origin. So let's parameterize the line segment. So it's 2 plus 0 minus 2t, and 1 plus 0 minus 1t, and 0 plus 0 minus 0t. Okay, so what do we get? 2 minus 2t, then 1 minus t, then 0, where t goes between 0 and 1. And then we need r prime. So what is this? Negative 2, comma, negative 1, comma, 0. Okay, so let's just again quickly annotate. Right, so this is x, this is y, this is z, x prime, y prime, z prime. So now we're ready to set up the line integral. Okay, so again, we're calculating the work over the third segment. So that's the integral over C3 of f dot dr. And so we integrate from 0 to 1. The vector field again is is y0z. Right, so y is 1 minus t, and 0, and z is 0. Okay, so then let me just annotate so it's clear what's going on here, right? So this is y0z. Okay, dot r prime is negative 2, comma, negative 1, comma, 0. Okay, so now we're ready to calculate. So the dot product, these two components are 0, so we just can get negative 2 times this, which is negative 2 plus 2t. And so the antiderivative is negative 2t plus 2t squared over 2, evaluated from 0 to 1. So plugging in 1, you get negative 2 plus 1. And then plugging in 0, you get 0 and 0. So overall, negative 2 plus 1 is negative 1. Okay, so that's the work over the third segment. And then finally, again, we're interested in the work over the entire triangle. So we just add up all our individual calculations that we did. So if you remember, W1 was 3, W2 was -2, W3 is -1. So 3 minus 2 minus 1 equals 0. So what happens that there was no work done over the triangle. So one thing to be careful about is that even though in this particular example it calculated to 0, it doesn't necessarily mean that if you start at some point and then when you go around the curve you end up back at the original point, that the calculation is always going to be 0. So it just happens that in this example that is the case, but that doesn't necessarily always have to be the case. Okay, so in this example we did a line integral over a 3-dimensional vector field, and also one where we had to split it up into separate components.